All right, boys and girls, what we have here today in assignment 7I is the last chunk that is in unit 7. And this one is a little bit more difficult to kind of understand. Um, Looking at this, what we have is we are not given an average and a standard deviation like we usually are given and to find things, but rather we have this n and this p. Again, what n represents is the total number of people or total number of elements in this system, and p is the probability of success. Um, R is very specifically the number of successes. Okay, so let's get into a couple of the formulas, and then we'll come back to these problems and be able to figure out these problems, and we'll get these taken care of. So first and foremost, let's go ahead and get our formulas. All right, so going with formulas that we should already know, we know that z is equal to x minus mu divided by sigma. All right, and so what that does is that gives you a z-score in which you're able to look up an area. So again, an example is you have this curve, and you have, x, z area, and say, for instance, you have this value right here. Let's say it's 5 or something like that, whatever the value is above the average. And I want to know what is the area to the left of it. So I turn that into a z-score. So I throw that into the formula right there, and this comes out to be, just some rando z-score. Let's say it turns out to be 1.02 or something like that. And so I look that up on the table, and I get 8461, I believe, is the result in that situation. And what that is the area to the left of that curve. So it is all this area to the left. Okay, no problemo. That is old news. We know how to do that given that information. However, today, we are not given a mu, and we're not given a sigma, okay? We're barely even given an x. All right, so formulas for today. The average can be considered n times p. Okay, so they do give us an n, they do give us a p. Again, n is the total number of things, p is the probability of success. All right? And sigma is n times p times q rooted. Recall that, let's change colors here. Q is 1 minus p. Okay, so that is a way that you can get that. So with that in mind, you can turn an n and a p more into that type of problem. You can get a average and a standard deviation from an n and a p. Okay, now that's half the battle. The other part of the battle is something like this. The problems that we are going to be facing is we're going to be facing a problem such as r is less than 5 or something like that. It'll look something similar to this. And so what this is this is a curve. Okay, actually, let me make this a even number. No, 5 is fine. 5 is fine. All right. So before, what we were dealing with is we have this value of 5, and we find everything left of 5, and everything's all good to go. Yay, hooray. However, when I'm dealing with r's, okay, very specifically r's, okay, you're dealing with something similar to like people or something like that. Something that can't be broken up. So what I'm trying to say is this. Don't think of a curve as being a smooth curve, but rather something similar to this kind of concept right here, right? Where we have where it's kind of like a histogram. Okay, it's kind of like a histogram. And so what the curve that we have is something that looks something like that. Okay, so kind of think of it in that sort of mind frame, right? Where the R isn't a straight up line. So where you have the number 5 here, we're looking for the letter 5. 5 is a bar. 5 is a bar. So if I want anything less than 5, that would mean I want the 4, the 3, the 2, the 1, 0, etc., etc. I don't want the 5 because it's less than 5. So technically the edge of the shading and the unshading, not shading, occurs right there, which is technically between the 4 and the 5, which is 4.5. And that is going to be that X that you use when you find your z-score, et cetera, et cetera, et cetera. All right, so my little way of thinking of this and the way that I do these problems is, put it down, R's get bars. R's get bars. And here's what I mean again, one more time. I draw my picture. I know that I want the number 5. So I make this little dash, I label that 5, and then I make a bar around that 5. I shade what I need to shade. So I want it specifically less than 5 in this case. And so I pay attention to where the edge exists. I see that the edge is just a little bit below the 5, so that would be 4.5. Again, you're dealing with halvesies. If the problem were a little bit different, let's say I want R to be less than or equal to, 3 or something like that. Again, I make my swoop. All right. I have the number 3 that is somewhere. I create a bar. And here I want R to be is less than or equal to. When it's or equal to, you shade in the bar itself. So the edge of the shading in this situation, notice how it's a little bit above the 3. So that's going to be 3.5. Give you another scenario here. Say I want greater than 4. Okay, 4 is somewhere, I'm not exactly sure. So is greater than 4 is over here, and I'll explain what you have to do differently. But the edge of the shading is right there, which is 4.5. Last but not least, what if I have like greater than or equal to 12? Right? So I have this number 12. I make my bar. This is greater than, so is greater than or equal to, leaving the edge right here, which is 11.5. Okay, so it's really critically important that you're able to identify the actual number that you're using. You're not ever going to actually be using the number that is written there. It's either going to be a half larger or a half smaller, okay, depending upon what shading you need to keep. So identify the edge of the shading and identify the number. Okay. That will kind of get you started. Let's go through some of these problems, and I will teach you some of the tricks and things like that that they might try to trick you with. All right, so here we go. All right, so here they give us an N and a P. So what we want to begin this problem with is we want to find our mu and our sigma, okay? So if P is 29%, that implies Q is what, 71%. Again, if you don't know, it's 1 minus P. We'll get you the Q. So that implies mu in this situation, which is N times P, is going to be 45 times 0.29. And sigma, which is N times P times Q, rooted. So N times P times Q square rooted. Okay, so we have our mu and our sigma. Let's understand the problem that we're asked to accomplish. So we have this number 17 that is somewhere. I make my bar around it, and I take a look at the question right here. So I want my R to be is greater than. So that is greater than or equal to 17. And so that leaves the edge right here, which is technically at 16.5, just a little bit below the 17. And so that is our X that we are using. Our X is now 16.5. Let's go ahead and continue on. So I need to turn that into a z-score, again, of 16.5. This is a z-score, so you round that to 2 decimal places. That's 1.13. And then you can go ahead and find the area of that. So 1.13, I look up on my z-table. All right, 1.13, 1.13, 8708. All right, now, here is where it gets a little bit tricky sometimes. Shoot. Sorry. Let me kind of clean up my mess here and explain what I mean by sometimes it gets tricky. All right, so actually, before I get to that, let me recap everything that I did. I begin the problem with an N and a P, and so what I do is I develop a Q, which is, again, 1 minus P. I develop my mu, which is N times P, and I develop my sigma, which is N times P times Q, square rooted. Okay, so that's just some math stuff. I go ahead and draw my curve, and I take a look. Oh, I'm looking at the number 17. So I make this little dash of 17, and I create this bar around the 17. I want my R to be is greater than. It's on the wide side. So again, if you don't understand alligators, okay, this, whatever side is, like, this distance between the sticks is very large. It's really big. This is the big side, okay? And then this is really teeny tiny, all right? The distance between those sticks is really small, all right? So we've got the big and the small. So I want my R to be bigger than the 17. Okay, I want my r to be bigger than 17. All right. So r is bigger than, so that's to the right. So if this is a number line, 0, 1, 2, 3, 4, 5, 6, 7, this is 17, and I want all the stuff bigger than 17, and then that bottom bar is or equal to. That means I darken in the bar. So I create the 17 dash, create the bar. I want the r to be is greater than or equal to. So that leaves the edge of the shading and the not shading to be right here on this red line, which I notice is just a little bit below the 17, thus it's 16.5. If it were a little bit above, it would be 17.5, but this is a little bit below, 16.5. So that becomes my x in this function right here. So I develop that into a z-score, x minus mu divided by sigma, so just using these numbers and my 16.5. Develop that, look at that. Now, here's where it gets sometimes, not all the time, but sometimes gets tricky. When I looked this stuff up on this table right here, which I was supposed to do, notice that this always, always, always gives you, quote unquote, the area to the left. Okay, no matter what I look up, this always gives you the area to the left. So if I go back to my picture, though, I don't want the area to the left. That's exactly what I don't want. So this area of 8708 is what I don't want. So this is an incorrect answer. This gave me all the area to the left. Again, if I were to kind of draw in what 8708 is, it gave me all of this area. I don't want that area. I want the area of that green region, which I shaded. So a hint, again, on what we have to do in this situation. Again, not all the time we have to do this, just when we find the shading that we don't want, is understand that the area underneath the entire curve is 100%. So in this very specific case, where I have the 17, I want is greater than or equal to, creating this edge, what I just found, okay, what I just found is this is 87.08%. Okay, this is 87%. So what I need to do is I need to find the area of the green region, so that would just be 100% minus that 8708. Again, you don't always have to do this, because sometimes you do want the area to the left. In this case, I don't. So in this situation, I have to take 1 minus this 8708, and that will get me 1292. That is the area that I want in this situation. Okay, a lot of stuff there. Hopefully you kind of start to get the hang of it here a little bit. Okay, let's take a look at number 2 here. Okay, a gym, open gyms show that 35% of the students are allowed to show up. So the probability of showing up is 35%. That implies 1 minus P would be 65%. Coach Mirage asked 40 students, so the total number he had to show up was 40. Okay, so what I'm going to do is I'm going to develop my mu, which is n times p. So n times p is straight up 14. Sigma is n times p times q square rooted. So n times p times q square rooted. Okay, let's understand the question that is being asked. So here's our curve. All right, we have this number 10. make a bar around it, and I want my R to be is greater than or equal to. So that leaves the edge of the bar right here, which is a little bit below the 10, so that's going to be 9.5. That's the X that I'm going to be using. I am interested in the area. However, again, when I find this area, this is going to give me the area to the left, which is what I don't want. So what I'll eventually, at the end, I'll have to take this like 1 minus area kind of concept to get the area of the green that I do. Anyways. So the first thing that I need to do is I need to find this z-score of 9.5. Okay, so I have that z-score right there. Let me kind of get myself some working area here. And so that implies the area of 9 to the left of 9.5, I should be more specific. Area to the left of 9.5, 149, negative 149 is 0.681. 0.681. Okay, that is the area to the left. So this is the 0.681 that they speak of. Now, I don't want the area to the left. I want the area to the right. That's the shaded of the green. So what I have to do in this situation is I have to take, it's supposed to be writing blue, sorry, 1 minus that 0.681. That'll be the area that I do want. And that is the area, that's the probability that I was looking for. All right, next problem. SCQ would be what, 74%? 84%. Almost made a huge mistake right after that. All right, so mu in this situation is n times p. Sigma is n times p times q. Let's understand the question that is being asked. Here I want just purely the area to the left of 40, not or equal to, but just purely to the left. So that leaves the edge right here, which is just a little bit below the 40. That's 39.5. And notice when I look up this area, it will give me the area to the left, which is what I want. So I do not have to do this like 1 minus kind of idea in this problem because I am finding the area that I want. Okay, so this will get me exactly what I need in this situation. Okay, so I find the z-score, and again, I'm working off of 39.5. So I have a z-score of 0.11. Zero 0.11, 5438. That is the area to the left. That is what I wanted, so that is the answer. All right. And number 4, how these problems are written is notice how the n is the exact same as the previous problem. The p is the exact same as the previous problem. That implies that the q is the same. And what that ultimately implies is that the mu is still the same and the sigma is also the same. So you don't have to do that mathematics anymore. And the problem is very similar usually, but again, you need to look at it because it is just a little bit different. Okay, here again we have the number 40, but notice that this time it is less than or equal to. So this time the bar gets shaded. So if I take a look at the edge, notice how it's a little bit above the 40. So this is going to be 40.5. So it's almost the same thing as the previous problem, but in the previous problem it was purely less than the 40, so it was 39.5. Here it involved the 40, so that means it's at 40.5. So the z-score, I'm investigating 40.5 in this situation. So I have 0.28 in this situation. So 0.28, 6103. Notice that that is the area to the left of that line, which is what I wanted. So that is the answer that I want. I don't have to do the 1 minus sort of thing. Okay, the last type of problem that you'll see in this type of setup is where you're finding the probability that R is between two different things. Okay, so again, one more time, we are provided the same n and the same p as the previous problems. So that means mu is still 38.88. Sigma is still 5.7148. And here is the problem that we are asked to figure out. All right, so we have this number of 35, and we have this number of 40. What we're trying to figure out is R is between 35 and 40. So R is between, it's bigger than the 35, and it's less than the 40. In this situation, it is or equal to the 35, so that means I shade the 35 box. And it is also or equal to the 40, so I shade the 40 box. So the edge of what is shaded and not shaded is right there, and right there. Those are the cutoffs. This lower one is a little bit below the 35, so that's at 34.5. The upper one is just a little bit above the 40, so that is 40.5. All right, so those are the X's that we are using. Okay, also one more trick that you can do is I've done all the information, I've done all the work for that 40.5. If we still have the same mu and the same sigma, that means we're going to have the same z-score and same area and all that stuff. So I already know the answers to the 40.5 stuff. This was 0.28 and 6103. Okay. So again, how you find the area between two things is you find both of the areas and then you subtract the big from the small. So the only part of that equation that I don't have right now is the information about the area to the left of the 34.5. That's the only information that I don't have. So that's where I'm going to pick up this problem. I'm going to find the z of the 34.5. Again, make sure you round to 2 decimal places. I find the area to the left of that 34.5, and so this one is associated with negative 0.77. So negative 0.77 there, 2206. So again, if I'm asked to find the area in between two things, what I do is I have to take the big area minus the little area. So that is exactly where my shading is. I want the area between my two blue bars that I created. So to get this area, I'll have to take the big area, which is the 6103, minus the small area of 2206. Boy, it gets a little funky when I try to write in the corners here. So again, that was 6103 minus 2206. And that's the area between. Okay. The other part of this assignment is not the same. I believe the very next assignment, J, is dealing with all of this, but I think the rest of this is review. So let me just kind of whip through this as fast as I can. So compared to a normal distribution for population, what differences would you expect when you construct a sample distribution? Okay, so remember, a sample is like that, and population is that. So I have to describe how a sample is taller and more narrow. So samples have so I'm going to say it's taller, so that is a larger relative frequency around the mean. And I'm going to say it's more narrow, so it has a smaller relative frequency. Or excuse me, a smaller standard deviation, I'm sorry. Okay, what will happen to a sample distribution curve as the sample size decrease? So this is one that I have to incorporate the formula. So this is the standard deviation of the sample, which is given by this formula right here. So if the sample size decreases, n gets smaller, I'm taking this n and I'm making that smaller. I notice that the n is a denominator, so that's ultimately a division. So if I divide by a smaller number, my answer will get larger. You have to have this mathematics as part of your answer. So if the answer gets bigger, again, this answer is a standard deviation. So that means that we will get a larger standard deviation. And if that happens, that implies that we have a smaller relative frequency around the mean. Okay, then we actually have some of the problems. This first one is a straight up X problem, so we don't have to do any funny business. We can just go ahead and straight up solve our question here. So we have numbers of 9 and 14 on here, and we want to know that X is between 9 and 14. So we have the number 9 and we have the number 14, and we want to find the area in between this. Let's begin with the 9. So the z-score of the 9 is x minus mu divided by sigma. So 9 minus 11.3 divided by 2.2. Again, round to 2 decimal places, so negative 1.05, and then the area associated with that, negative 1.05, negative 1.05, here we go, 1.05, 1469. Okay, so let's go ahead and repeat this process with the 14. And so now I need to find the area in between those two. So that means I am whoa, geez. So what I need to do is I need to take the big area minus the small area. Number 9 is pretty much the same question. However, you have to get a new standard deviation before you get that going. So the standard deviation in this case is sigma divided by the root of n. So in this situation, that's 2.2 divided by the root of 5. Okay, so I have this new standard deviation, then the process is pretty much the same, just with a different standard deviation. Get some area to work with here again. So I have the two areas and I want to find the area in between, so I have to take the big minus the small. Okay, last but not least, they're asking why was the x bar greater than the x? Well, because x, well, some fancy calligraphy. Fancy. All right, it's because x bar is a sample. And what does that mean? That implies that samples have a taller, so they're a larger relative frequency around the mean. And a smaller standard deviation.